Alors, avant de commencer, je tiens à remercier nos commanditaires. Tout d'abord, notre partenaire OR, Solutions Consortec, qui commandite l'enregistrement vidéo de nos conférences, comme vous pouvez le lire sur la note installée pour les équipements destinés à cette fin. Notre partenaire argent, l'Université de Québec à Montréal, qui est l'hôte du sommet 2017 de l'observation de la Terre. Et enfin, notre partenaire bronze, l'Ordre des arpenteurs géomètres du Québec, l'OAGQ, qui est aussi, colloque après colloque, un fidèle partenaire de l'AGMQ. Alors, sans plus tarder, je voudrais partir avec la première conférence. La conférence va être en anglais. Aussi, je vais transférer en anglais pour le bénéfice de notre invité. So, the conference will be presented by Martin Wallace from Okanagan College in British Columbia. Mr. Wallace?
Hello, everyone. My name is Martin Wallace. I'll be presenting in lieu of Kenichi Sugihara from Gifu Keizai University in Japan. Kenichi is my research supervisor for my honors. And our work is on the automatic generation of 3D terrain models by straight skeleton computation. Oh, perfect. So our work starts with generating 3D town models based on digitized building footprints. And you can see here is a generated 3D town model. And it continues on into generating terrain. So these maps can be used for disaster prevention, such as post-earthquake town reconstruction and large-scale earthquake countermeasure. 3D town models will be constructed on the area where the town could be escaped from tsunami and landslide. So, the objective of our research was 3D terrain models on which town models can be constructed and are automatically generated from key contour lines by straight skeleton computation. Oops. So related work. In SIGGRAPH 2006, Mueller and Wonka created an archaeological site of Pompeii and a suburbia model of Beverly Hills. And, oops. And related work number 2 is CAD and GIS software. You can see here from Autodesk Knowledge Network, 3D maps, everyone knows them. But these maps assume that there is a 2D map in which every point is associated with elevation data. Depending on the elevation of the points, these can be created. So our work does not assume that, and we're able to generate the 3D models based on a few sets of points. Straight skeleton computation is a method of representing a polygon by topological skeleton, similar to some ways to medial axis, but different. But differs in that the skeleton is composed of straight line segments. Oops. So here you can see the shrinking process of a straight skeleton. So it's defined by a continuous shrinking process in which the edges of the polygon are moved inwards, parallel to themselves, at a constant speed. Each vertex of the polygon moves along the angular bisector of its incident edges. This situation continues as long as the following event does not happen, either an edge event or a split event. In an edge event, the edge shrinks to 0, making its neighbor's edges adjacent. And in a split event, an edge is split, and the reflex vertex runs to this edge, splitting the whole polygon. So here you can see the beginning of a straight skeleton computation. And this would be a building roof generated from straight skeleton computation. So there we go. So for simulating mass granular flow, we first generate the terrain based on a set of contour lines, and then we generate a 3D town model based on building footprints. And then 3D simulations using Newtonian physics can be simulated in a semi-realistic environment. So map contours are receded when the altitude increases. If a receded contour is crossed by itself, then a contour polygon is divided. Contour polygons shrinking at the constant speed, causing split and edge events. And since they're monotone polygons, this can be computed in n log n time. Straight skeletons are defined as the union of pieces of angular bisectors traced out by polygon vertices during a shrinking process in which edges of the polygon move inward parallel to themselves. So these points here have been generated by the straight skeleton computation, and then using Delaunay triangulation, we're able to generate terrain models. So this is done using recursive programming. So Delaunay triangulation to points on shrinking contour polygons at split or edge events and in between events. And then B-spline curves from these polygons, Delaunay triangulation to points on the B-spline. This is some 3D generated terrain. So the target of our automatic generation module is, this is an example of Mauna Loa with 300-meter elevation contour lines. So this is the straight skeleton computation followed by the Delaunay triangulation, and then using primitive objects, we're able to, in a 3G module, we're able to generate the terrain and apply textures to them. This is another example here. So this is another example of Sado Island. It's an image from Google Earth stored in ArcGIS. And using the straight skeleton followed by Delaunay triangulation, we're able to generate this 3D terrain rapidly using only contour lines. So the contours are receded when the altitude increases. If a receded contour is crossed by itself, then a contour polygon is divided. And another example of the Delaunay triangulation happening on Sado Island. So generation of the 3D terrain geometry by assigning triangle primitives to triangulation patches, automatic texture mapping onto the triangles. So this is step-by-step of the shrinking polygons. So a shrinking polygon just before a split event, and then when the split happens, it's split into 2 polygons, and then again and again, and then the Delaunay triangulation is applied to the points generated from the straight skeleton computation. So the position of a node is given by the intersection of 2 angular bisectors, and one is from the reflex vertex, the other is between the intersected edge and one of the 2 edges incident to the reflex vertex. There's a not very good image of a 3D town model. That's the end. Any questions?